We know that Newton discovered gravity when an apple fell into his head. But why didn't the apple fall through his head? To explain what I mean, we must look at another great physicist, Ernest Rutherford.
In his experiment, Rutherford fired positively charged alpha particles at a thin gold foil. If you look at the experiment from above with the gold foil here, and the detection zone here, we can see that most of the particles went straight through the gold foil, as if it wasn't there. This suggested that the atom was mainly empty space.
The difference between the nucleus and the nearest electron count of an atom is so big that if the nucleus of a hydrogen atom was this apple, the nearest electron would not be where those geese are, but would be at the horizon.
Surely that's enough space for the apples to go through me. Actually, Rutherford also found that some of the particles were deflected, and some even bounced back. This suggested a positive charge, as the alpha particle was also positive. As we now know, in atoms, the nucleus is positive due to its positive protons and neutral neutrons. Therefore, some of the particles were going straight through, some of them were being deflected, and some were bouncing back. But wait, if protons and neutrons only are inside the nucleus, then shouldn't they repel? Okay, so apparently there's something called the strong nuclear force, which is responsible for this. It kind of acts as a glue between the protons and neutrons inside the nucleus. So if we draw a graph of the force required to keep them together, and here we have the attractive force, we would get something like this, with this being the distance between the two particles in femtometers, which is 10 to minus 15 meters. So this is around 1 femtometer, and this is around 1.5 femtometers. In this analogy, we have two bar magnets. These poles are the same as these poles. Therefore, if you try and bring them close together, they will repel each other. The Velcro here is a strong force. So if you try and bring them close together and bring them close enough with enough energy, they will stick together, overcoming the electromagnetic force. The complete graph actually looks something like this, with this being the repulsive force. So beyond an even smaller distance, the strong force is repulsive between the nuclei. But wait, that's so weird, right? So is the strong force some sort of elastic band? To understand the strong nuclear force, we must first brush up a little bit on our particle physics. Okay, so you have protons and you have neutrons. These can be split up into even smaller particles called quarks. Each of these has 3 quarks. Now these quarks have properties, just like with coin flips. Just like the head part of the coin doesn't necessarily have a head on it, these quarks' property names don't actually mean anything. These quarks in protons and neutrons, which are known as hadrons, can be in one of 2 states. They can be up or they can be down. Protons have 2 up quarks and 1 down quark, while neutrons have 2 down quarks and 1 up quark. When particles come close to each other, they experience a force. There are specific fundamental particles which allow for the reaction with a specific force to occur. For example, when 2 negative electrons meet, they experience electromagnetic repulsion. Since photons are the packets of the electromagnetic force between the electrons, these are exchanged when the 2 particles meet. This same process occurs when a proton and a neutron meet. Now remember, the proton is an up quark, a down quark, and another down quark, while the neutron is an up quark, a down quark, and another up quark. The only difference is that when these 2 meet, a reaction takes place. This down quark emits a gluon and moves here, while this up quark emits a gluon and moves here. So the final configuration is this. Wait, I've seen that somewhere before. So you have an up quark, a down quark, and an up quark, and here you have a down quark, and an up quark. That's the same as that, and that's the same as that. The neutron has switched places with a proton, and they are held together by the gluon that's been released between them. This process can be simplified like so. A neutron turns into a proton, and a proton turns into a neutron, while the gluon is exchanged, keeping these particles together. And in a way, yes, the strong force is sort of like an elastic band. Since this gluon is pulling this neutron this way, while this gluon is pulling the neutron this way, there's a sort of elastic thing going on. It's a bouncy effect. We call this dynamic equilibrium. A strong nuclear force is keeping the protons and neutrons together within a nucleus, giving it an overall positive charge. This is a very strong electromagnetic charge, so if you try and bring an apple atom close to one of my nuclei, the positive charges from these will simply cause them to repel. However, if you do happen to have supersonic apples around, then you will need to overcome the strong nuclear force, for which you need huge amounts of energy, given by the equation E equals m, which is the mass, times the speed of light squared. It is simply not possible to reach these sorts of energies simply with an apple falling from a tree. This is because the strong nuclear force is 10 to the 37 times stronger than the force of gravity.
The gravitational force is simply too weak to overcome the electromagnetic propulsion of the atoms. This is why the apple does not fall through my head. However, my head can go through the apple with enough force.